After many attempts to print an airflow amplifier using the kind of tolerances I was used to using in 3D printing, 0.2 or 0.3 millimeter, and getting pretty average results, I had the bright idea to actually Google what size airflow gap these typically have. Turns out it's more like 0.05 to 0.1 millimeters. With this in mind, I set out again, soon finding the slicing software automatically ignores any gap less than 0.1 millimeter and treats that as one solid thing, so that's my limit to work with. To get a baseline and calibrate my expectations, I did another standard venturi type airflow amplifier that I was first introduced to at my last job, just with a smaller diameter nozzle this time. As with my initial tests, the results were average, getting around 6 meters per second of suction. Moving on to my hybrid designs, sticking with the venturi shape I was used to, but shifting the air inlet type to that of a traditional airflow amplifier, I started with the air in positioned in the same place as before, just prior to the reducing cone. Better results with this, about 11 meters per second. Next up, I tried moving the air inlet to the end of the reducing cone. Unfortunately, this trial was a failure. I had printed this on my P1S, and it couldn't handle the 0.1 millimeter gap and closed it fully, leading to no airflow whatsoever. The rest of my prototypes were printed on my H2S, which seems to handle the 0.1 millimeter gap quite well. I haven't had it close the gap on any of those yet. Continuing on with this type, I moved the air inlet into the throat of the venturi. This resulted in better airflow than the standard venturi, but worse than the first hybrid. Finally, for this type, air inlet moved into the expanding cone of the venturi. Fairly similar results to the last one. Next up is the more traditional airflow amplifier shape. Nothing to write home about with this one really, either. Middle of the pack performance again. Finally, the 0.1 millimeter gap version of the type I had the most success with in my earlier tests. This one taking advantage of being able to entrain the air more completely on both the inside and outside of the ring. Significant improvement maintaining flow above 19 meters per second, with the next best version only getting 11 meters per second. I now have a clear winner for final development and refinement. The next hurdle I'm going to face once I've finalised the design is making this thing conductive. Because it's intended to be used in hazardous areas for flammable vapour extraction, it can't break continuity when earthing the vapour line, which probably means electroplating it. Trying to cast this thing and have something usable at the end would be a nightmare. Or a probably quite expensive option would be to laser sinter it out of metal. Just did a quick check on PCBWay's site, but they don't currently offer laser sintering of metal, though it looks like they plan to in the future. For now, I think I'll be going the route of electroplating.